My name is Yuri, Yuri Farias da Silva, and I will present the work named MultiObjective Optimization of Reinforced Concrete Buildings with Estevão Alencar Bandeira, Yuri Farias da Silva, and Valério Silva Almeida as authors. This is the agenda of the presentation, in which it will be talked about the introduction, then the optimization process, then the numerical application, and finally the conclusions with acknowledgements, reference, and authors after. So, in the last decades, great advance occurred in the development of structural design, in which many software were able to automate almost all steps of the design process, like structural analysis, dimensioning, and detailing. However, the stage of the structural placement remains manual, with a high dependence on the designer experience and intuition, demanding lots of time without the guarantee of reaching the most economic solution. Although this theme became relevant to the academic field, it lacks realistic approaches because of its high complexity, mainly due to the number of constraints when designing a building structure. With that in mind, this work is the seed of an artificial intelligence model that automatically seeks for feasible structural conceptions without any user interference. For that, the genetic algorithm technique was used as the optimization methodology, in which it searches for column positions that reduces the global cost of the building structure, such as concrete volume and steel weight. The optimization process is divided into 5 steps that they will be explained in the next slides. They are the reference mesh, the generation of the building structure, the structural analysis, the structural dimensioning, and the objective function. Well, due to the imposed architecture, a reference mesh is generated in order to create a nodal network in which each node will be a possible position for a column allocation. All nodes are both vertically and horizontally equidistant, and they are associated to a Cartesian coordinates. This is an example of a reference mesh with 9 nodes in the vertical and 11 nodes in the horizontal. Okay, with the nodal network ready, the genetic algorithm starts. It will randomly select a predefined number of values from the reference mesh to allocate the columns of the building. The beams then are generated after the columns, both horizontal and vertical lines that cross each column until the boundaries will be a beam. The boundaries of the architecture will also be beams. All elements have predefined cross-sections, and the number of floors and its heights are also predefined. This is an example of a structure generated with the randomly selected columns 2, 51, 80, and 84. In figure 2, it is possible to see the lines that crosses each columns until its boundaries. Well, in order to perform this structural analysis, vertical loads are added to simulate a real building. Then, a model developed by Almeida and extended by Aquino, based on the finite element method, is used to extract reactions and internal loads of every element. With this output data from the structural analysis, now it is possible to dimension each column. For that, the Newton-Raphson numerical method was used in order to obtain the coupled equilibrium equation for each column cross-section, and thus its volume of concrete and steel weight, making it possible to calculate the total amount of material for the whole building structure by these two equations, where PT is the total weight of steel, PV is the total weight of all beams, and PP is the total weight of all columns. Likewise, Volt is the total volume of concrete, Vol V is the volume of concrete of all beams, and Vol P is the volume of concrete of all columns. Finally, the total amount of each material is obtained, but volume of concrete and steel weight doesn't speak to each other. So it is necessary to convert them into the same unit. That is done by multiplying each one by coefficients in order to obtain their cost in Brazilian reals. And this is the objective function of the genetic algorithm. And it is trying to minimize, and this is the objective function the genetic algorithm is trying to minimize, where f is the objective function, p1 and p2 are coefficients. These 4 steps are repeated until it finds the minimal value of the algorithm or if the algorithm reaches the maximum iteration, as we can see in this flow chart. After meeting the stopping criterion, the best solution is reached. Here, to show the conceptions, a numerical application is presented, so we can see how the model works and to analyze some results. For this example, a rectangle area of 15/8 meters, the model will search for the most economic structural solution by randomly selecting 8 columns to generate the whole structure. Other parameters are given. The number of nodes in the horizontal and vertical is 15 and 8 respectively. And the building will have 2 floors of 3 meters high. In this figure, we can see how the reference mesh will look like. And it has 120 nodes. With that, the simulation resulted in almost 9,000 Ks over 63,000 of seconds, something close to 18 hours. The optimized solution can be seen in the next figure, in the next slide, which resulted in 1.92 cubic meters of concrete and 611 kilograms of steel. Those prices used as coefficients were obtained in SINAP, a Brazilian website, and the total cost of the structure was about 3,600 Brazilian reals. Here we can see how it looks like, the structure of the random selected columns. So to make a comparison, a hypothetical conventional solution was simulated with the same parameters. And we can see in the next figure, in the next slide, and the columns was symmetrically placed and was placed in corners. The result was about 2.16 cubic meters of concrete and 874 kilograms of steel, totalizing more than 5,000 of Brazilian reals. Here the hypothetical example of a traditional or conventional structure that we adopt. Both results can be seen in details in this table. And we clearly see the optimized solution achieve around 28% lower cost over the conventional one. This is the evidence that of the benefit of the structural optimization. You can see here we have very few cost in the optimized solution. Now this chart shows the cost over the iterations. It is possible to infer that the behavior of the structural optimization tends to reduce its cost over time, thus improving its performance to find the optimal solution. So, with the numerical application, it was possible to see the relevance of this work. It was possible to reduce 28% of the total cost without any user interference. And this is the main goal of this work. Also, the use of genetic algorithm is justified by the number of cases generated compared to the total number of possible combinations, which would take days to perform such optimization. Furthermore, this work considered only column elements for the optimization, and the next step to this work is to take into account beam materials amount. Also, it is necessary to consider architecture limitations such as door, windows, etc., which will be done in future works. The present work was performed with the support from National Council of Scientific and Technological Development, CNPq. Thus, the authors thanks to the institution support for their work development. Here are the references, a little about the authors, and thank you.